Now, dear student, chapter number 10, mechanical properties of fluids. And so we have the topic for the discussion here. Already we have discussed the equation of continuity. Now here I am just making the expression that mean regarding to the energy of a fluid in a steady flow. So same how as we are just making the concept of the mechanics. So even I am just asking the one of the general question to the student that what are the some types of the energies possessed by an object whenever it's making the movement from one place to another place, even in the vertical direction, that mean reaching to a certain height. So the answer probably you have that the kinetic energy is there, potential energy is there, and even you are just making the concept of the density that is associated with the particular material body is there. So whenever we are just discussing the concept of the fluids are there, or it flows through a that mean a portion of a pipe or whatever that open space, so it contains the sum of the energies are there. So how can we rectify them, and how can we find out their formulas, so we can apply them in the part of a different Bernoulli's the different theoretical aspects like the Bernoulli theorem, like the Torricelli law of flux, and the same how at the so many concepts are there where we can use this one energies of the flowing liquid. So here I am just starting them one by one. So here I am just discussing only the three types of the energies, that is called the kinetic energy, potential energy, and the pressure energy. Okay, and these energy we can represent in the sense of the per unit mass, per unit volume, and the per unit weight, or whatever the concept we are using in the different application, that is very true for us. As I am just asking, I am just making the simplest formula, that is half mv square. So what actually it is? M is the mass of liquid we have, v is the velocity of liquid we have. So here we are just assuming the density of the liquid also, that rho is the density of liquid, because we are just assuming the incompressible liquid. So throughout the volume the energy density of the liquid is the constant. Okay, so here we are just representing them in the three parts. So first I am using the concept of the kinetic energy per unit mass. So I am just making the simply division of that part. That means half mv square is to be divided by m. So I am just getting the formula of that v square by 2. So this is the first representation we have. Okay, so use this one concept. Now the B, kinetic energy per unit volume. So per unit volume, that means make the concept, that means kinetic energy per unit volume is the V is there. So we are just getting that half mv square, and here we have the volume concept of the volume we have. So I am just writing in the part of the rad is there. So little bit, so you will make the difference between the velocity, and little bit I am just making the turning of the that mean edge of the velocity. So here we are just using the simplest formula, rho is equal to m upon v. So I can make the simplest concept, that is or half rho v square. So this is the part of the that mean kinetic energy per unit volume we have. Now the C, that is called the kinetic energy per unit weight, and the weight having the formula that is called the mg is there. So kinetic energy per unit weight is there, that is called the W weight. That means half mv square is to be divided by W is equal to mg, and it comes in the part of the v square upon 2g. And same how the v square upon 2g sometimes called the velocity head is there. Okay, so you just keep inside your mind, somehow we are just getting, so v square upon g is called velocity head is there. Okay, so this is the simplest that mean representation. So must pay the attention, v square by 2, half rho v square, and the v square upon 2g. These are the three basic formulas regarding to the kinetic energies per unit mass, per unit volume, and per unit weight. Same how I just making the another changes also. So here we are just assuming the concept, the energy possessed by liquid by virtue of its position above the surface of the earth. So definitely it can't be moved upward by its own, but we are just taking the concept of the pipe is there which having the certain heights from the surface, that mean height from the surface. So whenever the concept of the height is added to a liquid, so the potential energy is associated with it, and we have the basic formula of the potential energy, that is called the potential energy, that is called the mgh you have. Okay, so same how we are just making the conversion of these, that mean of this energy. Now, dear students, we have the potential energy per unit mass. So I am just dividing it by the mass. So I am just getting the GH. Potential energy per unit volume mgh is to be divided by volume is there. So I am just using rho is equal to mass upon volume is concept is there. So I am just making the changes, that is rho gh. Now the potential energy per unit weight can be executed in the part of mgh. So the h is called the potential head we have. Okay, so now the next we have. Now the simplest that will define the energy by virtue of its pressure is called the pressure energy. So we are just assuming a simple movement of a water inside a tube, and here I have made the concept of the piston is there, which is available in the area of the cross section. That means area of cross section of piston, that is called the A is there, and on which the water is making the force. Okay, so whenever the pressure is coming on a piston, okay, so it makes the movement, that is from position A to A dash is there. Okay, so it comes and travels through a distance of the x is there. So what is the kind of the work done by the, that mean work done, that mean by the liquid on a piston we have, so we want to calculate it. So here we have the liquid of a density rho is applies a pressure P, so it moves, that means piston moves through a distance x. So what is the kind of the work done? So we have the basic formula, work done is equal to, that means force into displacement, force into displacement, and we are just assuming this one force in the part of the pressure. So because we are, and already we have the general formula, that means pressure is equal to force upon area is there. So I can write that means pressure into area, and the displacement, that is called the ax is there. So here we are just assuming the formula of that uh, work done, that is called the P, and area into length makes the concept of the volume. Okay, so this is the kind of the volume we have. So this is the meaning of the work done whenever the liquid makes the pressure on a piston. So the work is stored in the term of the pressure energy of the liquid of the volume V is there. Okay, so this is the simplest formula we have. Now we are just representing in the three portions. So here we have this work done by a liquid stored in the term of the pressure energy of liquid of volume V. Okay, so the work done will is equal to the pressure energy, that is P into V. So first representation we have, that means pressure energy that is called the per unit volume, P into V is to be divided by B, that is called the P. Okay, so this is the simplest representation we have. Now the second we have, that is called the pressure energy per unit mass. So we are just getting the P is equal to P into V is to be divided by mass, and the rho is equal to M upon V. So I can write that P by rho is there. So this is the concept we have. Okay, now third formula we have, that is called the pressure energy per unit weight we have. So we are just getting that P into V, and W is called the mg is there. So we can write it that P upon rho g. So this is called the pressure head we have. This is in the term of that pressure head we have. So these are the, that mean the general formulations we have discussed. So by any concept, that mean energy per unit volume, you are using the energy per unit mass, or you are using the concept of the per unit weight. So through any kind of the concept, you can discuss the Bernoulli and the other portions of the Bernoulli theorems. Okay. So if I am just asking to you that what kind of the energy is associated with the flowing fluid, so you have the very good answers regarding to them. Okay, so you can use the concept of the half rho v square is there. Okay, you can make the concept of the rho g h is there, and even you can make the concept of the, that mean v square upon 2g. So you can utilize the formula in the different manners whenever you are just discussing these portions of a behavior of a incompressible non-viscous fluid. Okay, so this is the completion of the lectures. So you must complete these two portions. So on behalf of these portions, we will discuss the larger problems of the that mean fluid dynamics. Okay, thank you.